Hi, my name is Gang Tang. I'm in Central for Quantum Software and Information, University of Technology, Sydney. In this talk, I want to tell you about my joint work with Joshua Grochow and Youming Qiao, average case algorithms for testing isomorphism of polynomials, algebras, and multilinear forms. So the problem of polynomial isomorphism has many applications in different areas, such as cryptography. Well, what's the problem of polynomial isomorphism? Let's look at an example to understand this problem. Suppose we have a polynomial of degree 3 over a finite field of order 5. Here we choose polynomial f x y z is x cubed plus 2x squared y plus 3xy squared plus 4xyz. And then we have an invertible matrix A, also over F5. Next, we apply A to F and we can get a new polynomial G. Just transform each variable to a linear combination of x, y, z and column of matrix A. For example, we look at the first variable. That is x plus 2y plus 3z. Then we have a new polynomial G. Okay, in this example, we say that f and g are isomorphic. The question is, if we only know f and g, how do we find such invertible matrix A? Then let's look at the formal definition of this problem. Suppose we have f be a field and x is a set of variables, and G, L, and F are invertible matrices over field F. Then we have an invertible matrix A sending F to G, and each new variable is a linear combination of each column of A and the original variable. In this problem, it asks if given two polynomial f and g in fx, if we can find such invertible matrix A such that A sends f to g. In the literature, this problem is also called the polynomial equivalence problem. Okay, here we have some motivations to study polynomial isomorphism. Partnering in Europe in 1996 first proposed to use polynomial isomorphism as the security basis of authentication and signature protocols. If consider our previous example as a crypto system, in this system, the public keys are f and g, is two polynomials. And the private key is invertible matrix A. The direct way to attack this protocol is to compute the private key A. And also, Aguirre and Saxena studied polynomial isomorphism from the computational complexity. They related polynomial isomorphism with graph isomorphism and algebra isomorphism. And Qiao studied some special instance of PI. In addition, Bouygues and other researchers studied polynomial isomorphism in multivariate cryptography. Well, so why we start PI? Because despite the above works that we introduced, but little progress has been made on algorithms with rigorous analysis for general polynomial isomorphism. For instance, Qiao's algorithm, it only works in the multilinear setting, namely when polynomial f and polynomial g are isomorphic to a common multilinear polynomial h. The algorithms from variate cryptography are mostly heuristic. In other words, these algorithms need unproven assumptions. But these works contain several nice ideas and insights, and their implementation show practical improvement. So let's take a look at the complexity of this problem. In worst case, we say that f is arbitrary. In average case, we say that f is random. In degree 1 and degree 2, this problem is polynomial time solvable. But in degree 3 or more, it starts to get harder. So Agro and Saxena in 2006 proved that it was at least as hard as graph isomorphism. And once we get to degree 3 or more, the best algorithm that we have is still essentially brute force. So we have over a finite field of order q, you get running time q to the n squared. And in the worst case, that's best way. In the average case, in this joint work between myself, Joshua Grochow, and Youming Qiao, we showed that in average case, you could get this down to q to the n instead of q to n squared, but still exponential. Okay, this is the first result of our work, which is described as below theorism. We have such a average case algorithm running in time q to the n that decides whether f, polynomial f and polynomial g are isomorphic for the most polynomial f. Okay, now we have some definition of cubic form and symmetric trilinear form and alternating trilinear form. Firstly, cubic forms are closely related with symmetric trilinear forms. If we have a trilinear form phi, is a map from f to the n times f to the n times f to the to f. If for any permutation sigma in S3, we have phi u1, u2, u3 is equal to phi u sigma 1, u sigma 2, u sigma 3. We say this trilinear form is symmetric. Also, if whenever two arguments of phi are equal and phi evaluates to 0, we say this trilinear form is alternating. If given a trilinear form phi from f to the n times f to the n times f to the n to f, and an invertible matrix A in GLNF, and A sends phi to phi A inverse U, A inverse V, A inverse W. The trilinear form equivalence problem asks, if given two trilinear forms phi and psi, does there exist an invertible matrix A in GLNF such that A sends psi to phi? We also have some motivations to study alternating trilinear form equivalence. The first motivation comes from cryptography. If we want to store a symmetric trilinear form on fq to the n, we need n plus 2 choose-3 field elements. But if we store an alternating trilinear form on fq to the n, we only need n choose-3 field elements. The difference between n plus 2 choose-3 and n choose-3 could be practical. For example, if we choose n is equal to 9, we have n plus 2 choose 3 is equal to 165. but n choose 3 is equal to line choose 3 is 84. This means that in the authentication protocol of Pathway, if we use alternating trilinear forms instead of cubic form for n is equal to line, one saves almost 1/2 in the public key size, which is an important saving in practice. We also have motivations from comparing symmetric and alternating bilinear form, because in bilinear form condition we have the alternating is easier than symmetric. And because of the alternating trilinear form equivalence can be used in some areas of mathematics such as representation theory, is one of our motivation. Okay, let's look at the complexity of alternating trilinear form equivalence. We have below theorism as our result 2. We proved that the alternating form equivalence problem is polynomial time equivalent to the symmetric trilinear form equivalence problem. Thus, we established the complexity connection of cubic form and symmetric trilinear form and alternating trilinear form because of cubic form isomorphism is polynomial time equivalent to symmetric trilinear form equivalence over finite field f over characteristic lot 2 or 3. Therefore, though these two problems are polynomial time equivalent, these problems may result in crypto systems with different efficiencies for a given security level. And we also compare with bilinear form, because in bilinear form condition we say that alternating bilinear form is easier than symmetric bilinear form, but in trilinear form we say that is polynomial equivalence, is polynomial time equivalent. Well, here is some main idea of our average case algorithm. Recall that we have two cubic forms, f and g, and we want to find isomorphism T such that T sends G to F. Firstly, if we enumerate all n by n invertible matrices, we require q to the n square iterations. So we enumerate the first r rows and columns. Okay. At most q to the ORN minus T1 in GLNQ, such that T is equal to T1, T2, and T2 is a block diagonal form. The first step we enumerate the first R rows and R columns. Actually, we enumerate the T1. And then we focus on T2 is equal to block diagonal form such that including identity of R by R and matrix R. So we focus on find this matrix R because if we find R means we find FT2, means we find T. Okay, we have observation and R sends 8 quadratic forms to another 8 quadratic forms. Inspired by Li and Qiao, we have if we have F1 to F8 is are random quadratic forms in FQ, then with high probability, there are at most Q to the N matrices T, such that T sends Fi to Fi for I from 1 to 8. We adopt it as symmetric matrices if we fix R is equal to 8. So because this lemma, we can enumerate R in time Q to the ON. Okay, let's review this algorithm. Firstly, we have input is two cubic forms F and G in FQ. And we have an isomorphism T in GLNQ sending G to F. The first step, for I from 1 to R, we have E1 to ER span ER. And we also have Fi is spanned by ER plus 1 to EN. And the isomorphism T maps EI to UI. We say that UI is the first R columns of isomorphism T, and TFI is equal to V is a subspace of FQ to the N. Where that T1P be any matrix satisfies T1EI is equal to UI and T1FI is equal to V. Because of T is equal to T1, T2, so we have T2 is T1 inverse T, and satisfies that for I from 1 to R, T2EI is EI and T2FR is FR. Okay, we first enumerate matrices of form U1 to UR and R plus 1 to EN. Let's find the image of EI. Okay, then we need to enumerate the image of FR. And we have the number of complement subspace of dimension R is equal to Q to the R times N minus R. In step 1, we enumerate the T1. So in step 2, we focus on T2. Actually, we need to find matrix R. Suppose F is equal to summation of alpha ijk xi xj xk for I from 1 to R. We define Fi is equal to summation of alpha ijk x1 xi xj xk for the R plus 1 is less or equal j is less or equal k is less or equal n. Similarly, we define hi. For the I from 1 to R, we have T2 send hi to Fi. This is the key observation. So T2 sends xi to xi. And for j is from R plus 1 to n, we have T2 sends xj to a linear combination of xk. Because this key observation, we can construct a series of quadratic forms C1 to CR and D1 to DR, and R sends D1 to DR to C1 to CR. C1, Ci and Di are quadratic forms for I from 1 to R. Okay, if C1 to CR are random polynomials, then the number of those are sending D1 to Di to Ci for the I from 1 to R, and R can be computed in time Q to the ON because of the above lemma. Finally, we have some concluding remarks. Our result also have impact on patterns crypto systems. The security parameters need to re-evaluated. For example, if we have n is equal to 10, q is equal to 5, then the system can be broken as our algorithm roughly involves 5 to 10 instead of 5 to 100. In result 2, we proved that alternating trilinear form is polynomial time equivalent to symmetric trilinear form equivalence problem. And in the proof, we go through tensor isomorphism problem, and we use tensor isomorphism completeness class introduced by Grochow and Qiao in ITCS in 2021. Okay, that's all. Thank you.